So like she mentioned, my name is Zach Cartwright. I'm a food scientist by training. My background's in wine microbiology. But when I was done with school, I started working for AQUALAB. You might know us as Meter Group, but we are rebranding right now. But we've always had the AQUALAB brand, and I have talked with many of you, and it sounds like a lot of you use our devices. Even in Steven's video, there was an AQUALAB 3 in that video. So when I was first asked to come and talk, Grace asked me to focus on packaging and how water activity relates to packaging. But when I sat down and started to put this together, I realized that there's a lot of different ways that water activity really helps the pet food industry. And so I wanted to make this presentation a little bit more broad and go over all the ways that you could be using water activity. If you don't use it now, you certainly should, and I hope that's clear after this presentation today. Or if you have a water activity meter, there may be other things that you could be doing with it. And so I want to make sure that you're getting the most out of your current device. So when I talk to people in the pet food industry, some of the common or the reoccurring challenges that I heard are things like precision of current moisture methods. A lot of pet food manufacturers, or any manufacturer of any food, generally uses an oven method, or maybe a titration method, or maybe a moisture balance. And there's a lot of inherent variability with all of these different methods. It's really hard to get consistent results. And because of that, you have to set a spec that's lower than you want. So I hear a lot of companies that really want to maximize the moisture content in their products for profit. And the reason for that is water is simply the cheapest ingredient in any formulation. And so the more water you sell in your product, the higher your yield in revenue. But it's really hard to do that if you're using a method that isn't very precise. I hear a lot of companies, of course, wanting to avoid any mold and microbial growth. I was able to find some numbers on just how much pet food has been lost or recalled or thrown out due to mold and microbial growth, and we'll look at some of those numbers. A lot of companies want to be able to predict a shelf life, so understanding how long your product or products can sit at a certain temperature or certain humidity without having a change in water activity that will result in microbial growth or maybe some type of texture change. And this is actually something that we can predict pretty accurately if you have the right data and you know what calculations to do. This kind of goes hand in hand with choosing packaging. So there's a lot of supply chain issues or a lot of companies with green initiatives that are changing packaging right now. And a lot of time when I meet with food scientists or people in R&D, I ask them how they decided on their packaging, and they don't really know. They don't really have data to support that decision. They just go with whatever their packaging manufacturer recommends. And a lot of time what's recommended is over packaging or sometimes under packaging, but there are some ways to make a data-driven decision about the packaging that you're using. And then finally, when I talk to R&D scientists, they're always under a lot of pressure to accelerate formulation processes and come out with a new formulation and do this as quickly as possible. And there are some tricks that I want to show you today that I think could help you, especially for your R&D teams. So all of these challenges, they're all related to the water that's in these products. And when it comes to water, there's basically two ways that we can think of water. The first one is moisture content. So this is a quantitative measure. This is what most people in the pet food industry are familiar with because it makes the most sense. It's really easy to think a quantity of water. If you were to take every molecule of water out of your product and put it in a glass, this would represent the moisture content. So to calculate the moisture content, we have to take the wet weight minus the dry weight after an oven method and divide by the wet weight and multiply by 100. So this gives us a moisture content in terms of percent. But the problem with a moisture content method is there's no way to determine if it's accurate or not. So everybody uses different methods and it's really hard to compare them to each other. Even if you're using an oven method, if you leave that product in the oven longer, it's just going to continue to go down in weight over time. So it's really hard to know exactly when to stop that type of test. And because of that, we don't know if your reading is accurate or not. There's also a lot of variation with moisture content, whether it's different testing methods or incorrectly calibrating a moisture balance. I almost never see them calibrated correctly, or a user error. Anytime you interact with the sample, you introduce error. And so if you're trying to measure moisture content in an oven and you're putting it in and weighing it and putting it in and weighing it over and over, this allows there to be a lot of error, and then you have a lot of variation in this method. So moisture content, though, is still important. It's something that we need to understand, especially if you're thinking about yield and revenue. So moisture content has its place, it has its value, but there's another way to think about water, and that's water activity. So water activity, bless you, has been mentioned several times today, but I bless you, it's okay. Water activity has been mentioned a lot, and even in food science courses and classes, I see water activity kind of mentioned, and then you go on to the next subject. I don't see a lot of people spending as much time on water activity as I think they should, because there's a lot of value behind this measurement, and if you ask somebody to define water activity, a lot of time they can't really define it, and it's a little harder to understand. But the way to think about water activity is to think about it as unbound or free water. So if we took all of that water that we collected in the last example that was in the cup, if we took a sponge, if that sponge represents the structure of your pet food, and we put that sponge in that glass of water, then it's going to soak up a certain amount of water, it's going to bind it, and then everything that's remaining, any unbound or free water, this would represent the water activity. So this is water that's free or that's available for microbial growth or physical changes or chemical reactions. So you can think of it that way. I think that kind of paints a good way to think about it. A better or a technical definition of water activity is it's actually the energy of that water. So it's actually a thermodynamic principle. It's something that we calculate using Gibbs free energy equation. And we do that by measuring vapor pressure. So we talked about this in one of the small groups earlier. But basically, our devices measure vapor pressure, and then we use that to calculate a water activity value. Water activity ranges from 0, something that has no energy, all the way up to 1, something that has the same energy as pure water. Water activity is a really high resolution measurement. It's something that we can measure down to plus or minus 0.003. AQUALAB makes the most accurate meter that's out there. And part of the reason for this is that we have standards for water activity. So moisture content, again, there's no standard. We don't know if it's accurate or not. But water activity, we have a whole range of standards that we can verify and use these to make sure that our instruments are being giving a correct value. And then that water activity, it's a driving force. It can be used, again, for microbial growth. It can be used for certain chemical reactions. So reaction rates are going to be different at certain water activity values. And then it can also be used for physical changes. So if you have a caking and clumping problem for a powder, or if you have a snack food that's staling, or some other type of physical change, we can generally relate this back to a certain water activity and then know exactly what water activity to avoid. So overall, water activity is really helpful for safety and quality. So each of these measurements kinds of has its place in terms of water measurements, and it would be really nice if we could take both of these and combine them on a graph, and in fact we can. So if we take a graph and if we have water activity on our x-axis, again going from 0 to 1, and then if we have moisture content on the y, this can help us understand the relationship between these two measurements. So if we use the device that I showed you downstairs, it takes a single measurement. It takes a single water activity reading, and there is a corresponding moisture content, but in order to know that, we need to map this entire relationship, and we can do that. It's called a moisture sorption isotherm. So an isotherm is the complete relationship between water activity and moisture content, and it's at a certain temperature. So usually we run these at 25 degrees Celsius. So the reason that this isotherm is so helpful is because, as you can see on this graph, as you move up the isotherm, you might start to get enzyme activity or microbial growth. There are certain reactions, like Browning reactions, that has a peak reaction rate, usually around 0.6 water activity. Lipid oxidation is kind of an interesting curve. Lipid oxidation actually increases at a really low water activity. So if you're using freeze drying or any drying process and over drying, you're actually going to encourage lipid oxidation for that product. So lipid oxidation has a lower rate, usually around 0.4 water activity. And then finally, there are some physical changes. They're not shown on this graphic, but physical changes can also occur on this as well. So a lot of clients that I work with, they use this graphic and they use an isotherm to understand the relationship between safety and quality of their product, but also yield and revenue. So if we have an isotherm, then we can set the correct spec for a product. So basically, to make this isotherm, we have a really unique process called a vapor sorption analyzer. And we take a product and we put it in a closed chamber, very similar to the AQUALAB device downstairs. And then we slowly change the environment. We either add wet air or dry air over the top of that sample. And then we take lots of data so that we can create the entire curve. Did you have a question? Oh, I thought you raised your hand. So here's just some examples of what an isotherm may look like. So this is for a grain-based formulation versus a grain-free, just to give you an idea of what these may look like. So every formulation, every product, even every ingredient is going to have its own unique curve. So if we looked at different ingredients, these are just a range of ingredients. For example, a pork meal, a chicken meal, barley, a grain-free mixture, and a grain-based mixture. So I'm just highlighting that depending whether you're looking at an ingredient or a formulation, each of these is going to have its own unique moisture map. Okay, so that's just kind of my quick background. So now we know a little bit about water activity, moisture content, and we understand what an isotherm is. So let's come back to this list of challenges and just kind of work through them one at a time. So the first one is precision of current moisture methods. For current moisture methods, a lot of companies in the pet food industry, they just accept that there's going to be a wide range in moisture content, usually because they just don't believe or they haven't seen that improvements are actually possible. So they're generally using oven methods or a moisture balance, like was just mentioned, or they're really wary of implementing something new because moisture content has been used for a much longer time. Whereas water activity, we came out with the dew point sensor in 1989, and it's slowly starting to take over other industries. But again, I still see a lot of industries or people in the pet food industry not using water activity. I also see a lot of companies that try NAR. NIR, it doesn't have as good resolution as I think people think it does. And a lot of NIR equipment, it needs to be calibrated very constantly, and I almost never see that done. So if you use NIR, it does have some challenges as well. So what we did is we asked some of our clients to try to graph water activity versus moisture content using their own moisture method. And so this is kind of a typical result that we see. You just have moisture content kind of all over, and we don't see that isotherm that I just showed you. You know, there should be that sigmoidal curve that we just saw, but if you try to do this using a separate moisture content method, it's almost impossible to do, and you're lacking precision and accuracy. The results are kind of all over the board. So to improve this, we need to think about the precision of the moisture content method. So this is just from a 60 sample library that we did a study on. We're looking at percent residual standard deviation. So this is how far the measurements are from the average or from the predicted moisture content. So a lot of moisture balances are usually several percentage points away from that. So you're getting all of this information under the worst conditions. It was close to 7%. This was for a device that wasn't being calibrated correctly. If you use a reference oven method, these are generally close to 2%. So if you're producing a pet food that's 14% moisture content, this generally means that you need to give yourself a 2% buffer. You need to set your target at 12% because you know some of those are going to be high and you know some of those are going to be low. So to improve this, we could use an isotherm. So there's the isotherm being shown in gray. And if I use an isotherm and measure water activity first, and then use this isotherm to relate it back to moisture content, I can really improve the precision of that moisture method. So this can help me to be precise and more accurate. So this is how we do it. We basically take an isotherm data set, which is shown in green, and then we develop a model for it. So this is called a DLP model. It just stands for double log polynomial model. It's a model that we developed. There's like 100 different isotherm models that have been published, but this is one that we use really often. And that model has coefficients related to it that we basically send to you so you can use it on your device. So once you have this model, we can really improve the precision using an AQUALAB 3, for example. So the AQUALAB 3 has a residual standard deviation of about 0.4% versus some of these other methods. So it's almost 5 times better than the oven and almost 10 times better than some of these moisture balances. So that's the graphic I was talking to you about. So once we do this, once we improve the precision of our moisture method, this is when we can start to maximize the moisture content for profit. So the goal, usually when we meet with a pet food client, this is what they want to do. They have an average moisture content. Let's say in this example, they're producing a kibble at 9%, and they have a pretty wide range in moisture content, with some of the kibble going above the safety limit and leading to microbial growth. The goal is 3 things here. The first thing we want to do is reduce variation in moisture content. The second thing is that we want to increase the average moisture content. And then the final thing is we want to avoid any product from going above that safety limit so that we're not having any microbial issues. So this is what it would look like graphically. Let's say in this example, we're able to reduce the variation and increase the average moisture content by just 0.5% and prevent anything from going above the safety limit. Okay, so this is the goal. And this is what it looks like in real life for one of our clients that we worked with. So this is client, we'll just call them client A. They have a pretty big annual production, 360,000 tons, and their previous moisture content target was 10%. So what we did for this company is we produced the isotherm, we helped them set a new spec and reduce their variation, and we showed them that they could actually safely produce this product at 10.4%. So just a very small change, but it's going to have a really big impact on yield and revenue. So because of this, now they are using more water than ingredients, and they were paying a lot for those ingredients, about $800 per ton. So instead of using ingredients, they're now using water. And for this specific product, the yield increase was over $1 million. So even though it's just a small change in moisture content, it can have a profound effect. And someone was talking to me earlier about even a 0.1% change in moisture content. If you're able to do that for all of the products that you produce, it can quickly pay for the device and really help your company. A lot of companies that I've worked with in the pet food industry, they generally have a 2% margin, and that's because they're using an oven. So they have to set a margin that's lower in case they're going to have products that are high. Because of this costs money over time. Every week that goes by, this is costing because you're not optimizing the moisture. So in this example, we're looking at cost on the y-axis and weeks. And every week that goes by, every week that you're not optimizing your moisture content, that you're 2% lower than you should be, this costs money. So we did a big survey for our clients. For clients that were making treats, this was costing them about $5,000 a week. If they were making kibble, it was costing closer to $11,000. And if they were making biscuits, it's almost $21,000, $22,000 per week. So every week that goes by, this is what we call the cost of inaction by not reducing that variation and increasing the moisture content. The next one that I want to go into is avoiding mold and microbial growth. There have been a lot of pet food recalls over the last 10 years. This was some data that was collected by someone named Susan Thixon, and I reached out to her to try to better understand exactly how she collected this data, and I'm still waiting for a reply. But this is what I was able to find. So between January 2012 and October of 2021, there's 327 million pounds of pet food recalled within the US, and the majority of this is due to microbial problems. So the number one reason, almost 50% of all recalls was due to pathogenic bacteria, and this was, of that 160 million pounds, this was 98% of it was kibble. Some of it was recalled due to aflatoxin, so this just is a toxin that's produced by fungi. This was about 60 million pounds, and then mold accounted for kind of a smaller margin than I expected, about 167,000 pounds. So regardless, there's just a lot of waste that's occurring, and if we want to improve a carbon footprint, then we just need to avoid waste and recalls. And a lot of this can be done using or thinking about using water activity. So water activity is directly related to microbial growth. You can use water activity to make sure that the kill step is working. So Venancio talked about HPP and having a water activity above 0.97 to make sure that it's effective. Or you can use water activity to make sure that your product is going to stay safe during its shelf life and not have any mold or microbial issues. So we can kind of attack this at the beginning or as that product sits on the shelf. Keep in mind that no pathogenic bacteria can grow below 0.85 water activity. This has been well researched. Even under optimal conditions, if you drop the water activity below this value, then no pathogens can grow. And there's no microbial proliferation of any kind if you go below 0.6 water activity. So a lot of times in the pet food industry, they'll either set a limit of 0.65 or 0.6 as the maximum for things like kibble. Keep in mind that water activity is not a kill step itself. So it's just another hurdle that we have in our tool belt. So you're not killing the microorganism. You may have something that's safe, but not necessarily sterile. So if there are spores there, if conditions become right, if your product becomes rehydrated, or if it sits in a high humidity environment and the water activity goes high enough, then you can start to have microorganisms that grow. So having something that's safe but not sterile. As those conditions change, if your packaging isn't the correct type, or if this sits out in an environment with a high humidity, your product wants to come to equilibrium with the surrounding environment, so that water activity is going to increase over time. So for example, if you made kibble and the water activity of your kibble is 0.55, and then you send it somewhere where the humidity is 65%, if you give that kibble enough time, it will eventually come to equilibrium at 0.65 water activity. So you can think of water activity being equivalent or interchangeable with relative humidity in that way. So this is just a graphic that I included, just showing different pathogenic microorganisms and their minimum water activity. So for each of these, if you go below this minimum water activity, these microorganisms won't grow. This is why there's a regulatory standard for foods of having a water activity of 0.85 or less for shelf-stable foods. So things like beef jerky, a lot of times producers are trying to get really close to 0.85, but make sure that they're not going higher to have these problems. Okay, next let's talk about predicting shelf life and packaging. So I went ahead and combined both of these together because they really go hand in hand. So to calculate a shelf life, you need to take into account three things for any product. You need to take into account the packaging. So this includes the surface area of the packaging, the mass of the product inside that package, and the water vapor transmission rate. So this is rate that water from the environment is going to move through your packaging and then interact with your product. The second thing we have to keep in mind are the storage conditions. So this includes temperature and humidity, as well as atmospheric pressure, which is going to change depending on your elevation. And then finally, we also need to know the sorption properties of the product. So we need to take the isotherm of the product and then turn it into a mathematical model. So once we have all of this information, we can put it into a calculator that we've developed. This is a shelf life calculator. It's based on something called Fick's Law, which has been published and there's studies out on it. And this is a calculator that can be found in what's called the Moisture Analysis Toolkit software. So I'm just going to kind of walk you through an example. So let's say that we have a 40-pound bag of pet food, and it's going to sit somewhere that's at 65% relative humidity. In this case, we're at room temperature and at sea level. We're going to put in the mass, it's 40 pounds. We're going to put in the surface area of the packaging and then our water vapor transmission rate. So this rate is something that can be experimentally determined, but it's also usually given to you by whoever your packaging provider is. They should know the rate for their packaging. From here, I'm just going to put in my water activity of the product. So let's say we're at 0.5, and then I need to put in a critical limit. This is a water activity that I never want to exceed. So I'm going to put in 0.6 because as I just showed you, if we go higher than 0.6, this is when mold and other things can start to grow. So these are my inputs. The last thing I need is my isotherm. Again, in the background here, the isotherm is being turned into some type of model. And then when I hit calculate, it's going to give me a shelf life. So in this example, it means I have 186 days until that initial water activity is going to reach the critical limit under these conditions and using this packaging. So the reason that this is really handy is because now I can go in here and change the conditions. Maybe I can try the most extreme conditions that I think my product will ever sit in, the highest temperature or the highest humidity, and understand how long I have to stay within my target water activity. Okay, so let's say that in this example, this is my predicted shelf life, 186 days, but it's not quite long enough. I really want it to be 1 year and stay within that water activity range. So what can I do? If I go back to the calculation, instead I'm just going to kind of turn the calculation around and determine the water vapor transmission rate I need in order to hit a desired shelf life. So this is a really good way to make sure that you're not under packaging or over packaging, that you're making a data-driven decision on exactly what water vapor transmission rate you need for that specific formulation. I also talk to companies all the time that are either changing packaging due to a green initiative by that company, or there could be a supply chain issues. So those could be reasons why you have to change your packaging, but need to understand, what's going to work for me. So in this example, the calculator looks almost the same. The only difference in this one is that I'm going to put in my desired shelf life. So I want to hit for 1 year, keeping it within my water activity range. Again, I'm just going to use my isotherm. And then this time, the output is the water vapor transmission range or rate. So I could take this rate to whoever my packaging supplier is, and then they can recommend the right type of packaging or maybe layers of packaging that will help me get to this rate. So one calculation that I'm not showing here is if you're using multiple layers, there is a calculation that we've worked on and finally released last year so that you can calculate multiple layers of packaging and understand what the combined water vapor transmission rate is. So you might need combined packaging if you're sending to certain locations in the US or outside the country. You might need to add another layer for certain products, but this would also help you to understand what rate you need to hit to stay within your ideal range. Both of these calculations that I just showed, they are determined based on water activity and setting a critical limit, but shelf life isn't always related to water activity in that exact way. So the calculations that I just showed are really good for microbial growth or maybe a texture change. But what if your shelf life is dependent on a chemical change? What if it's lipid oxidation or a color change or loss of an active ingredient or loss of a vitamin, something like that? Then there is another way to do this. It is a little bit more intense. It takes some more data collection, but it is something that can be done. So I'm just going to kind of walk you through it quickly. So basically, in that same software, we developed what's called a chemical stability tool. You can use a chemical reaction rate to determine shelf life, and it's based on the Arrhenius equation. So again, just something that's been published, that's used a lot. We basically just put it in a software and made it easier to use. This requires a lot of data collection, so you have to have humidity chambers, or you can have us do this for you. But basically, you need to analyze your product at 2 different water activities, and at each of those water activities, we want to collect data at 3 temperatures that are usually higher than room temperature. So we have to set up basically 6 different situations, and then we measure whatever you're interested in over time. So you have to have some way to assess color change or lipid oxidation or whatever that chemical reaction rate is. So we have to measure a change over time. But once we've collected all of that data, we can use a different calculator where the inputs are temperature, water activity, and a condition. And what I mean by that is, as a condition, you have to put in, for example, if 90% of an active ingredient remains in your product, or you can say 10% of this active ingredient has been lost. So you have to set some type of condition, and then the result is a shelf life, so you can quickly understand or predict a shelf life. You also get a Q10 value, so basically if you change the temperature by 10 degrees, this will tell you how that affects the reaction rate, and a QA value. This is if you change the water activity by 0.1 units, how that affects the rate. So you can do a lot of predictions for a chemical reaction rate if that determines your shelf life. It just takes some extra study and data collection, but I just wanted you to be aware that that's a possibility. All right, this is my last application. So accelerating formulation processes and also reducing time to market. So before you even make a new product, you can quantify and understand how moisture is going to move. You can predict what the equilibrium water activity will be. You can visualize what the isotherm will be. And then you can also predict the shelf life and start to think about your packaging decisions before you even make that new product. So this is going to work best for dry ingredient mixes, or if you're taking final products and putting them together. So let's say that you've produced several different types of kibble and you're going to combine them as one final product. If each of those different pieces or types of kibble have a different water activity or different moisture, then when you combine them, moisture is going to start to move among those different products. And we want to make sure that the final product is going to be safe and stay within a certain water activity range. So to do that, we have developed a mixing tool in that same software. It uses what we call DLP modeling. So let's say in this example, we're going to take 3 different types of kibble. For each of them, each of these kibble have their own water activity. This means they also have their own moisture content. And then we can also put in a mass ratio. So in this example, let's just say we're going to take equal parts of each kibble 1, 2, and 3. When I hit calculate here, it's going to show me the isotherm for each type of kibble. So you'll just see them labeled here. And then the software is going to tell us the combined isotherm. So you'll see it there in red. So before even making this product, I know what that final isotherm will look like. And I also know the equilibrium water activity. So if I give these 3 types of kibble enough time to come to equilibrium, the water activity in this example is predicted to be 0.52 water activity. It will also tell me the coefficients for the isotherm. I can take these coefficients and use them to predict the shelf life and think about the packaging. So I can take these and put them back into that calculator that I showed earlier. And then finally, I can also understand which way the moisture is moving between these different types of kibble. So it will tell you the moisture content for each type of kibble. So this is a really good way if you're constantly working on formulations. Basically, our clients that use this end up making their own isotherm library of all their different ingredients or different products so that they can sit down and maybe think about a new formulation or think about how a new ingredient is going to affect their final water activity or the shape of their final isotherm. So at this point, I hope I've shown that water activity does benefit the pet food industry in a lot of different ways, not in just packaging or just maximizing yield. So all of these challenges that we went over, each of them can be done using water activity. And I'm happy to answer any questions about each of them.